Good day, everybody. So we're looking at more linear transformation. So pull open section 3.3 and get MATLAB open so you can be ready to take notes. So I'll assume that you've paused the video and you're ready to go. So let's talk about linear transformations. And these are the ones that we see all the time in this course where we use all linear transformations. And so what's a nonlinear transformation? Well, y equals x squared, right? The graph of the function f of x equals x squared is not linear, so it is not a linear transformation. So these are just functions. So what does it mean? And I'm sorry, this should have been a plus sign here, right? Sorry about that. So it's linear provided that I can either add the vectors in the domain and then transform them, and I'll get the same thing as if I transform both vectors and then add the results in the range. If I get the same answer either way, and if I get the same answer if I do the scalar multiplication in the domain or after I've transformed the vector u, then I have a linear transformation. Okay. Also, one thing that's always true is the textbook is just awesome on this, and they've got some nice visualizations. So check out section 3.3 in the Margalit text and try to get a better idea of what's going on. Now, we're also going to talk about how to determine the behavior of the entire behavior of a transformation. And it turns out that what we need to do to see is to track what happens to the standard basis vectors. If we know what happens to the standard basis vectors, that's going to determine what happens to every vector, which makes sense because every vector in the domain can be written as a linear combination of the standard basis vectors. So a lot of times, though, the standard basis vectors are very easy to visualize and to see what's happening to them. So we're going to focus on that when we need to find out what a linear transformation does. Also, we have some common transformations. Okay, if I'm looking to transform all the vectors and I want to reflect them all across the x-axis. Okay, well, you see the matrix A here. And what's going to happen? It's going to leave the x coordinate unchanged, right? I'm thinking of multiplying, I'm thinking of this as the vector that I'm multiplying by, where I kind of have x as the x coordinate and y as the y coordinate. Well, you'll notice that the one in the top left of the matrix is going to leave the x unchanged, which makes sense. To reflect it across the x-axis, I don't have to change the x-coordinate, but the y-coordinate is going to become negative, which will in fact reflect it across the x-axis. And the same thing happens when I reflect across the y-axis. I need the negative acting on the x-coordinate. And then reflection through the origin does both of them, right? So it takes both the x-coordinate and the y-coordinate and makes them negative. Now these horizontal scalings, so if I'm going to scale in the x direction, then I scale the x-coordinate. And if I'm going to scale in the y direction, I scale the y-coordinate. Okay, and then the interesting one here is rotation by theta degrees. And this is the rotation matrix. And we use this all the time. And you just have to tell us what theta you want to rotate by. And then we have to do some trigonometry, right? We have to actually calculate cosine theta, sine theta, and so forth. Okay, well, that seems doable. Let's take a look at MATLAB for a moment. Okay. And so we have the reflection across the x-axis and the reflection across the y-axis. And so I entered those matrices here. And let's talk about what I said. I said the behavior of the transformation can be determined by what happens to E1 and E2, vectors E1 and E sub 2. All right, because they're the standard basis vectors in R2. So I went ahead and entered them. All right, so remember I2 will get me the identity matrix, and the 2 means the identity matrix for R2. And of course, vector E sub 1 is the first column of that identity matrix, and the vector E sub 2 is the second column, okay? And if we're going to reflect across the x-axis, we're using this matrix A sub x, all right? So we're just using this one, all right? And if we multiply the reflection across the x-axis, that matrix that does that, times E1, what happens? Well, it turns out that E1 is unchanged. Okay, so I take the matrix, multiply times vector E sub 1, and I get vector E sub 1, but that actually makes sense because E1 lies on the x-axis. So if I take a vector that lies on the x-axis and I rotate it, excuse me, I reflect it across the x-axis, it doesn't move, right? It doesn't change at all because it's sitting on the line we're reflecting across or reflecting through, depending on how you say that. I've heard it said both ways by different mathematicians. And then what happens to the vector E sub 2? Well, notice that, right? So if I have this coordinate axis, right? And I have, the standard x and y axis, right? So the vector E sub 1 has unit length and it points to the right, okay? And so again, if I'm flipping across the x-axis, this vector E sub 1 doesn't change, but what's E sub 2? Well, E sub 2 is the unit vector that points up. Okay, well, what happens to it? Well, it gets transformed. Why? Because it gets reflected across the x-axis, right? So now it's pointing down. That's why we have the negative coordinate there. So since it lies on the y-axis, it has to point in the opposite direction. So notice that its y coordinate is now negative. Okay, so in fact, this thing gets flipped across the y-axis, excuse me, across the x-axis. And that's a poor drawing. Sorry that that I'm not an artist. All right. Well, let's take a look at an example. So this will be the kind of thing that'll happen on a test or a quiz. You'll be asked, well, hey, create a transformation that the first thing it does is going to stretch vertically by a factor of 4, and then it's going to rotate by 270 degrees, and then reflects across the x-axis. And it's important that you realize that we need to do this in order. Okay, so it's saying do this first, right? Do 1 first, then 2, and then 3. Why is that important? Well, we can accomplish this by just creating the 3 individual transformation matrices that we need, but then we have to multiply them in the right order. Okay, so that's where order is going to matter. Okay, and we know the first and the third, right? Stretches vertically by a factor of 4. If we just want to run back up, stretching vertically by a factor of 4, we're like, hey, 1, 0, 0, K. Rotation by 270 degrees, we can get that. We have to calculate it, but we can get it, right? And then reflection across the x-axis. So the nice thing is these are easy. The vertical scaling and the reflection across the x-axis we know, and we can calculate the third one that we need. All right, so let's jump back here. And then the rotation matrix we need, let's jump back into MATLAB. All right. Here is the example question. And notice this. Let me actually take this and get a little room here and take the semicolon. So the semicolon at the end of these lines is suppressing the output. It's doing the calculation and creating these matrices. But let me actually show you what's going on here with A2, okay? And notice that we're not using cosine. If I used cos, C-O-S, it's assuming, MATLAB will assume that I'm using radians, that the angle measure is radians, okay? So cosine D, cos D, and sine D, that's degrees. Okay, so I get the option of using a slightly different function, and then I don't have to convert the degrees to radians. Right, this isn't a trigonometry course, but that's where we're using sine D, cos D, or cosine d, however you want to think of that function. And we get this nice transformation. Our A2 transformation is 0, 1, negative 1, 0. Okay, so that seems cool. And jumping back, there we go. 0, 1, negative 1, 0 is the correct rotation matrix. But here's the key. To get the order right, we have to remember that these transformations, even though we're calling them linear transformations, they're functions. Okay, they're vector valued functions. So to get them in the right order, I have to remember what I know about functions. And so if I'm going to evaluate f of g of h of x, what do I do first? I do the inside most function first, right? I got to begin with h of x. I evaluate h of x, put the result into g. I evaluate g of h of x and put the result into f. Okay, and the same thing is going to happen with transformations. So what they've asked me to do, they've asked me to do the first transformation and then the second transformation and then the third. Okay, so the order in which I'm going to do the matrix multiplication may seem odd. You may seem, oh, take the first matrix A1, multiply it by A2, multiply that by A3. No, we don't do it. We do them in descending order. Why? Because it's functions, and I have to evaluate the innermost function first. And then once I have A sub 1 times the vector x, then I take the result and multiply it by matrix A sub 2, and so on. So remember, it's just like there are functions. It's not just like functions. They are functions. Transformations are functions, so they behave exactly the same way. So to get this transformation, I need to do this matrix multiplication, which of course I'm going to do in MATLAB. Boom. Okay. So, and again, if I take these semicolons off, you can see the individual matrices. Sorry. I was trying to get, okay. Sorry, what is going on here? Oh, this has a problem. Okay, I think I have it right now. What was I trying to do? I was trying to show that the first matrix, A1, is a vertical scaling by positive 4. Okay, so the second one is this rotation matrix. And the third one is this reflection across the x-axis, okay? And when I multiply them in the right order, I get the matrix 0, 4, 1, 0. Okay, great. And we have that here. We're doing this matrix multiplication, right? And remember that we're starting over here with this matrix multiplication first, right? So we're doing the top row times the first column, and then the top row times the second column to get, right? And so we're going to get this result, and once we have this result, we're going to multiply it by A3. So, so the order is important here, okay? And let me get rid of the ink. So we do know the standard matrix. So I say associated matrix. It just makes more sense. I think the proper word in mathematics is standard matrix. So a transformation has a standard matrix, and that's fine. But the standard matrix is associated with the transformation. So I sometimes use my own term there and call it the associated matrix. But just letting you know, I think standard matrix is the more generally accepted term. But it's important to notice that this order is important. Let's do it in the reverse order. So I have that set up in MATLAB, getting rid of the ink and jumping over to MATLAB, right? So what if instead of doing A3 times A2 times A1, I start with A1 and do A2 and then A3, and you can see the result already. The result is the wrong matrix. This is not the correct transformation. Okay, the correct transformation in the correct order is right here. Okay. Now, what's going on? Well, so matrix multiplication is not necessarily commutative. So A times B is not equal always to B times A. Now, it turns out there are some times where this can happen, where you have A times B does in fact equal B times A. It's rare, but it can happen. So I'm not saying this is always true, that they're never equal. Okay, that's not true. Sometimes you will get the correct answer by multiplying in the wrong order. But don't count on it because it's rarely true. What's usually true is that when you multiply in the wrong order, you get the wrong associated matrix for the transformation you're trying to get. Okay, so that's how we work with these common linear transformations.